Great. All right. So our second speaker of the day is Gregory from who's going to be talking about enumerating 60 supergravities. So please, Gregory, go ahead.
Yes, thanks for the introduction, and thanks to the organizers for all their hard work. Yeah, so indeed, I'm going to talk about some recent work together with Yuta Hamada for the past year or so, working to understand 60 supergravities with minimal supersymmetry. And I'll present some results from earlier this year in which we enumerate all consistent models for some particular simplifying assumptions. So the plan of the talk, so I'll start with some motivation based on some progress that's been made in the past few years. I'll introduce or remind you of the low energy consistency conditions that we'll require. And then I'll give a taste of our numerical methods, so using some ideas from graph theory and graph algorithms as a way to deterministically and systematically enumerate these anomaly-free models. And then I'll present some targeted data for t equals 0 and 1. We're generating a landscape of consistent models from a low energy perspective, and then we can make a connection with the swampland program as well. And then I'll finish with a summary and some somewhat tangential thoughts on the finiteness in this setting. Okay, so as you all well know, absence of gauge anomalies is a very non-trivial constraint on chiral theories. So in particular, standard model and MSSM are familiar cases where the chiral spectrum at first glance miraculously cancels all of the gauge anomalies. And when we have dynamical gravity in the game, then dimensions 2, 6, and 10, so 2 mod 4, are very special in that they have potential pure gravitational anomalies, which need to cancel as well. And then maybe most importantly, in the past 5 years or so, there's been a lot of progress in string universality. So establishing in dimension 7 and above that there's an exact match between the string landscape and those models which are consistent with very general principles. So to my knowledge, this program is essentially complete in dimensions 7 through 10. And so the next logical place to go is to 6 dimensions. So this is a swampland seminar series, so I'm required by law to have concentric ovals here. For me, these are regions having to do with anomalies. So we have in the red region, those which cancel the local gauge anomalies. The blue region includes also the gravitational anomalies being canceled. And then within those, further still, we have the quantum gravity landscape and the string theory landscape. And so the name of the game is to understand which of these regions are finite, which are infinite, and maybe more importantly, which of the different regions actually coincide. So in the back of my mind for this talk, I'm going to have the blue and the green regions floating around. So because we're working in a low bottom-up perspective, I'm going to present results for the landscape in the blue region. And then near the end of the talk, I'll try and make a connection to the green region. Okay, so let's look at the consistency conditions. So with minimal supersymmetry in 6 dimensions, we have 4 types of supermultiplets: gravity, tensor, vector, and hyper. And for any model, we'll need to specify the following data. So we'll choose some integer number of the tensor multiplets. We'll choose a gauge group with the vectors in the adjoint as usual. And we'll choose some representations for the charged hypermultiplets. So I'll usually just restrict attention to the charged hypers, which are in non-trivial representations. This is almost enough to address the anomaly cancellation, as we'll see shortly. And an important feature of the super multiplets is these two-form fields. So I've called them B here. There's self-dual two-form fields and anti-self-dual fields. And their number have an important role in the anomaly cancellation. So before that, so I should say that I'm allowing the gauge group to be non-abelian, but with any number of simple factors and with any representation. So allow for fundamental and two-index symmetric and anti-symmetric, but anything else as well. Okay, so our consistency conditions. So as advertised, there are local anomalies that need to be canceled. We have the Green-Schwarz mechanism at our disposal. And in order for the anomalies to be able to be canceled, this anomaly polynomial needs to factorize. So here it's parametrized in terms of these vectors B0 and Bi, which are generating this lattice lambda. And all of the consistency conditions can be phrased in terms of this lattice. So because of this factorization, we get some data. So in particular, the irreducible terms are giving two constraints. One of them is some bound on the total number of hypers, vectors, and tensors. And the other terms, which are reducible, are specifying all of the inner products amongst these vectors, Bi and Bj. There are also potential global anomalies which need to be checked for SU2, SU3, and G2. But these are easily avoided, so let me not dwell on this. There's also what I call a unimodularity condition, which is that this lattice needs to embed into a self-dual lattice of this particular signature 1T. And so this is the avatar of Dirac quantization in this context. And then finally, there's what I'll call a positivity condition, which is that there needs to be a point in the tensor moduli space for which all of the gauge kinetic terms are simultaneously positive. And the point is that the inner products, the Bi, Bj, are computed just from the charged hypermultiplets, from the charged spectrum. And then all of these conditions can be checked without necessarily needing the vectors themselves. So just from the data encoded in this matrix, we can check these conditions. For example, the last condition, the positivity one, amounts to some constrained quadratic optimization problem that can be checked numerically. Okay, so I'm going to make some distinctions between these models. I presented the low energy consistency conditions that need to be satisfied. If a model corresponding to some choice of T, gauge group, and charged hypers satisfies all of them except for the gravitational bound, that's what I'll call admissible. If it satisfies also the gravitational bound, then that's what I'll call anomaly free. This includes also that unimodularity and positivity condition. And this, if you like, is what a low energy experimentalist would call perfectly fine model. But of course, if we're interested in embedding this into quantum gravity, then we should also impose some additional constraints that come from the UV. So later on, I'll talk about some swampland criteria that need to be satisfied as well. And that's what I'll call a fully consistent model. Okay, so our task, what we'd like to do is to enumerate anomaly-free models, do this in a systematic way. And in some special cases, we can do it in an exhaustive way where our list of models is complete. So what's been known previously for about, I guess, 15 years now, is that when the number of tensors is relatively small, then the number of anomaly-free models is finite. Now, for better or for worse, the way that this is proved is by contradiction. And so from this work, we don't necessarily know the extent of the models, how many there are, what their properties are. There's also been a lot of work going back about the same time in enumerating models in some special cases. So either with simple gauge group or with particular low dimensional representations for the hypermultiplets, or with small values of t. And so what we did in this series of papers, starting last year and continuing on in current work as well, is to bring these ideas to their logical conclusion. So in the 2023 paper, we described how you can generate models in a way that's almost agnostic to the value of t. You can generate models basically in a t-independent way. Today, I'm going to focus on t0 and 1, where we have more complete data. We allow for any hypermultiplet representations, and we allow for any gauge group with the only practical limitation that we have to omit some low rank simple factors. So no U1s, no SU2s, no SU3s, and no SB2s. Okay, so what is the perspective that we'll take? So the way that these models are described is very combinatorial. So it's helpful to think in terms of graphs, and actually more precisely in terms of what are called multi-hypergraphs. So the idea is that to each simple group and choice of hypermultiplets, we can associate a vertex in this graph. So here are the red points corresponding to SU8 and SU10 with some choice of fundamentals and antisymmetric hypermultiplets. And then the edges within this graph correspond to ways to merge these hypermultiplets to form bicharged matter. So in this example, it turns out that they're all bifundamental, but we allow for anything that's possible. Now, the multi and multi-hypergraph corresponds to the fact that several edges may connect the same two vertices. And in this case, we see there's an edge with one bifundamental versus two bifundamentals, and these will correspond to different physical models. Okay, so what's the point? The idea is that given any anomaly-free model, you can break it down into these constituent parts, but we can now reverse the problem and start with the simpler parts, the vertices and the edges, and now reconstruct models going the other way. And any admissible model can be identified with an embedding of a simplicial complex into this graph. So this example at the bottom, our simplicial complex is just a triangle, 3 vertices, 3 edges. And from this, you can read off what the corresponding models. Now, it turns out that in this case, the value of h minus v here at the bottom is far too large. So this model is not anomaly-free, but it is admissible, as I described. Okay, so actually what I've done so far is nothing more than translating the problem into this graph theoretic language. So it's a very combinatorial problem. And the point is that we can now adopt fairly standard graph algorithms in order to generate models in a systematic way. So the way that this goes is that you start just with your favorite vertex. And to this, you can add edges and vertices one by one and build up some tree of models that are ever more complex. And along the way, you'll find ones that are not only admissible, but also anomaly-free, satisfying the gravitational bound. And you also find models which are irredeemable. So they either violate one of the consistency conditions, or they have a value of h minus v, which is far too large to ever be salvageable. And then what happens in practice is that this branching process eventually terminates, and you are left with just a finite list of admissible models that you can weed out and be left with just the anomaly-free ones. Okay, so this procedure we've done, as I said, both for general T, where we do some randomized search, we can't, in practice, generate all of the models, as I'll indicate later. And we do it for small t, where the number of models actually turns out to be not only finite, but small enough that it's practical to enumerate all of them. Okay, so let's look at the data that results. So as I've said, we're omitting some low rank gauge groups, but otherwise we find that there's about 20,000 anomaly-free models when we have t equals 0. And you can imagine doing some statistical analysis on this list of anomaly-free models. So what I've plotted here, for example, is the rank of the gauge group going left to right, and the number of simple factors in the gauge group going up to 6. So the simple gauge groups are along the bottom row, and they eventually peter out at rank 23 with this SU24 theory, very simple hypers. And as you go to 6 factors in the gauge group, again, it peters out. There's just a handful of models that appear in that extreme, in this case, an SU4 to the 6th model with bifundamentals. There's also this somewhat curious spike when you have 4 gauge factors out to rank 24. So this is somewhat curious, but anyways, the gauge group is SU7 here at the extreme to the 4th with bifundamentals. And our methods, as I advertised, include not just bifundamentals, but any representation. So in principle, our list, or in fact, our list contains all the models which have, say, tri-fundamentals or quad fundamentals. And indeed, we find that these are exceedingly rare. So there's only 20 models that have hypermultiplets charged under 3 or more factors. So there's one example here, probably the simplest, which has a tri-fundamental for SU4, SP4 squared. Okay, so when we turn now to t equals 1, the number of models, again, it's finite, but it grows very quickly. So already over 500,000 anomaly-free models. And we expect that as you go to t equals 2 and 3 and up to 9 and beyond, the number of models continues to grow. Okay, so rather than talk about each of them individually, I'll just give some highlights. The model with the largest gauge group rank has rank 47, somewhat different than the models which I described for t equals 0. These are very symmetric when you get to the large rank or the large number of factors. Here, this is somewhat asymmetric. There's an SU18 and an SU6, so somewhat curious. Maybe more curious is the fact that this is really an outlier in the data set that we generate. So in this figure on the bottom, dimension of the gauge group left to right, and then the rank of the gauge group going vertically. And there's this single isolated point well above the others. So somewhat curious. Okay, so we allow for any gauge group, and that includes exceptional gauge groups, the largest of which is E8. And we find that there are only 3 models with hypers charged under the E8 factors. And they're all related by Higgsing. So the largest of these with the SO8, E8 gauge group, Higgs is down to the other 2. And in fact, this model was previously known in the literature. So earlier in 2023, this model was constructed using an asymmetric orbifold in string theory. So this, if you like, is a baby version of string universality, where just using anomalies and supersymmetry, we have 3 models with hypers charged under E8, and there's a one-to-one match with the string landscape. Okay, and finally, the 500,000 anomaly-free models that we have listed, they don't have these low-rank gauge groups, but we can nevertheless use our data to generate examples like this in the following way. So by Higgsing, you can build up examples with these SU2 factors in the example I'll describe. And in this way, you can find examples where there are hypermultiplets charged under up to 5 or 6, or even I think the record is 12 at this point, constructed by hand. Right, so in this example, if you take this fairly compact hypermultiplet spectrum, and you Higgs the G2 factor and one of the SU4 factors down to their maximal subgroups, then you find actually a very long list of representations which appear. And there's a very delicate interplay between the different representations, which ensures that this model is anomaly-free. And this also suggests that it would be intractable to generate a complete list with the SU2 factors included. Even if they all come from Higgsing, there's lots of Higgs branching patterns that can arise. Okay, so now we come to I guess what is the punchline. So what I've described so far is the bottom-up perspective where we're imposing these low energy consistency conditions. And now you can ask, how does this match on to the quantum gravity or the string theory landscape? And so to to begin this comparison, we looked at 3 swampline bounds. So the first of these is coming from the completeness hypothesis, where because we have these 2-form fields, there will be charged strings under the 2-form fields. And by introducing these into the background, there's an anomaly inflow to the strings that needs to be canceled. And so what was done in this 2019 paper was to look at the condition that arises from ensuring that the left-moving current algebra is large enough in order to host the required central charge. So this is some non-trivial bound that needs to be satisfied based on the assumption of completeness. More recently, in 2021, there were 2 additional bounds that were proposed, which limit the allowed hypermultiplet representations. And so this, again, is by considering these probe BPS strings and considering the marginal deformations that are possible on the world volume theory. So somewhat surprisingly, when you test our 20,000 t equals 0 anomaly-free models against these conditions, all of them satisfy all 3. So this is somewhat surprising given the non-trivial nature of these bounds. And it's an interesting question. It would be very hard to confirm, but my suspicion is that it remains the case even when these low-rank groups are reintroduced. Somehow anomaly cancellation is strong enough for t equals 0 that it knows about all of the UV conditions that it needs to. Somewhat differently, for t equals 1, we find that roughly half of the anomaly-free models are ruled out. And so we're currently thinking about matching those that survive, so they satisfy all the bounds, they're anomaly-free, matching those to the string landscape and known string constructions. Can they all be matched? Which of them can be matched? Are there interesting models that perhaps could be constructed that we can identify? Okay, so in the last few minutes, let me summarize and then make some somewhat tangential remarks. So I discussed the 60 supergravity with 8 supercharges and these consistency conditions that we require. So the anomaly cancellation, unimodularity, and positivity. I described briefly the graph algorithms, the way to phrase this in terms of graph theory and identifying simplicial complexes that can be generated iteratively in a way that ever more complicated models are generated from simpler ones. And then using these ideas, we generated complete lists with this minor caveat on the gauge groups, with which you can do statistical analysis, and we saw some highlighted examples. If you're interested in exploring the data, then have a look at our 2024 paper. There we have links to all of the data that's available. And then finally, checking the swampland bounds that I described against this list of anomaly-free models. The t equals 0 all satisfy the swampland bounds, whereas only half of the t equals 1 models do. So one might hope that these swampland bounds somehow continue to get stronger and stronger as the value of t increases. And indeed, that seems to be the case. So there are infinite families that appear when t is 9 or larger, and there's some infinite families where t grows unbounded. The expectation was that these string bounds in particular would kill off all of these infinite families. And indeed, in 2 papers, 2019 and 2021, all of the known infinite families were shown to be truncated to a finite number. Somewhat disappointingly, or maybe interestingly, there are some infinite families that we found recently which satisfy all of the swampland bounds, and they have t unbounded as well. And so we're currently thinking about what additional general consistency conditions, either swampland bounds or some additional global anomalies, would kill all of the infinite families and be left with just a finite number of consistent models. So this is our expectation, just based on the finiteness of the string landscape. Okay, so with that, let me thank you and welcome any questions.
Okay, so thank you very much for the very nice talk. So we have time for questions. So yeah, Michael, first you can go ahead.
All right, that was a really good talk. I just had a couple of quick questions. The local anomalies canceling and the gravitational ones, but sometimes they have global anomalies. They try to show that they don't exist. I think this has only been done in 10D for the supersymmetric, and then recently for the non-supersymmetric case. But you have so many examples that would be interesting if there was a case where you had the local anomaly canceling, but there was a global anomaly that didn't cancel or that didn't exist. So that,
indeed, yeah. So yeah, I agree. Yeah, please go on.
No, that was just a comment. I don't know how you would actually compute the global anomalies, but I know in 10D they've done this recently for non-supersymmetric, and years ago it was done in the supersymmetric case. But in all cases, when the local anomaly cancels, the global anomaly also canceled. But it would be nice. You have so many examples. There might be some there where that would be an additional consistency condition that you could look at.
Indeed, yeah.
And the other question I had is you left out the U1 factors and things like that. Maybe you could put them back with some Higgsing. But that might be interesting to do, because if you go back to the old Salam-Sezgin model, where he studied 6-dimensional supergravity, there was a very interesting spontaneous compactification that came out when he had a U1 factor. He did study some monopole backgrounds on S2. So again, in that case, you'd be looking for a condition where it would spontaneously compactify, and if there would be a stable one. That would be additional, consistency. Not as a consistency condition, but it would be an additional way of using these 6-dimensional models to try to get a 4-dimensional model. I think in Salam-Sezgin's case, he started with n equals 2 supergravity, so you started with n equals 1. And then he compactified, he got n equals 1. Maybe in your case, you would get n equals 0. But in any case, it would be very interesting to go back and look at some of those old papers in your new context, because you have so many new models. But I think in his case, he would need a U1 factor, though. to do what he did.
Yeah, that's very interesting. Thank you.
Okay, we have one question here from Ivano.
Thanks for the very nice talk. So I have a couple of quick questions. First, am I correct that you're not considering discrete groups or discrete quotients of these Lie groups? Because some of them
Yes,
can be excluded.
that's correct.
Okay.
Yeah,
And then I wanted to know how you handle technically the decompositions on, in all possible irreducible representations, since you don't seem to put any constraints on the types of representations that you use for the hypers.
Yes, so you're asking computationally, how do you include all of them?
Yeah.
Yes. So yeah, I left out some of the details, but indeed there are indeed. So there are some there are some group theoretic indices that can be computed in some automated way, so that's not a problem. In practice, what we do is these vertices in the graph. What happens is that when you include more exotic representations, if you will, is the value of h minus v for the individual vertices grows very quickly. And so what you find is that beyond, say, h minus v is 1,000 or 2,000, or you can go up actually quite high for, say, SU6 or SU7, even the fairly small groups. You can generate these vertices up to some large value of h minus v, do the computation, and then look at which vertices actually end up in an anomaly-free model. And what you find in practice is that around 300 or 350 or so, there's a sudden cutoff where they just no longer appear.
In practice, you only have tensor representations of reasonably low ranks. That's what you're saying.
Yes.
Okay.
And so, yeah, so actually, this is one of the reasons that including SU2 or SU3 is so difficult.
Yeah.
Is because there are so many representations of low dimension.
Right. Okay, thank you.
Yeah, thanks for the question.
Okay, so it looks like we have no further questions. So let's first thank Gregory again for the very nice talk.
Thanks.